We care about the goodness of fit of the models we estimate. And instead of using the R square to assess the models, we're going to use the adjusted R square. Why? Because the R square increases as we add more x's. Differently, the adjusted R square takes into account the above and penalizes the measure as more x's are added. So let's look at an example. We can compare the summary of mod 1, and we need to use summary to get the output that has the adjusted R square, the R square, and the F step. And we see that the adjusted R square is 0.1196. We can look at the other model we estimated that included cattle lot. And what we find if we compare the adjusted R square is that this one is better because it's higher. So if we compare both, we can conclude that mod 1 is better as its adjusted R square is higher. Next, we study the joint hypothesis testing using the F statistic. As a reminder, we have seen the F statistic when we use summary within the output of summary, and that F statistic tells us if our estimated model is better than a model without x's. But we can use the joint hypothesis testing to test whether the coefficients of two or more explanatory variables are zero. In our example with the Brazilian data, we can test whether the coefficient on cattle lot and the coefficient on the price of milk during the rainy season are zero. Just as a reminder, this is the model we're using, and we can simply use linear hypothesis function. We pass the name of the model, and then we say what we're testing to be equal to zero. Notice that we still kept the study region as one of the x's. The output from that test reveals that the F statistic for this joint hypothesis test is about 73, and the corresponding p-value is below 0.001. Thus, we can reject the null hypothesis that both coefficients are zero at any level of significance commonly used in practice. We should always use a heteroscedasticity robust version of this F test, which is going to lead to the same conclusion, but the way to do it is we simply add this last part. We add that y dot adjust must be equal to HC1. The result, we see a change in F, but the p-value is still below 0.01. So we can also reject the null hypothesis and say that our model should include both of those x's. Always use this heteroscedasticity robust F test as the homoscedasticity assumption doesn't hold usually. The last topic for this week is model specification for multiple regressions. Choosing a regression specification, in other words, selecting the variables to be included in a regression model, is a difficult task. The goal is clear: to obtain an unbiased and precise estimate of causal effect of interest. We always should consider omitted variable bias, that is, to avoid possible bias by using suitable control variables. We look at economic theory, we look at previous research to inform us on what variables we should control for in our models. The adjusted R square tells you whether the regressors are good at explaining the variation of the independent variable in the sample. If this number is near 1, then the regressors produce a good prediction of the dependent variable in that sample, in the sense that the variance of the OLS residuals is small compared to the variance of the dependent variable. If the adjusted R square is nearly 0, the opposite is true. For this course, this is what we're going to use. There are more things to consider when we look at adjusted R squares. There may be models where the numbers are lower and they may still be okay, but for the level of this course, this is what we're going to be using. The adjusted R square doesn't tell you whether an included variable is statistically significant. The regressors are the true cause of the movements in the dependent variable, whether there is omitted variable bias, and whether you have chosen the most appropriate set of regressors. Now, let's look at three models within our Brazilian data. We're going to have spec 1, spec 2, spec 3, and each one is building from the previous. So in the first model, we have price of milk during the rainy season, cattle lot, and then two dummy variables for regions. Spec 2, we add pasture, and spec 3, we add family in addition to pasture. We gather the robust and their errors. The only things we change here is the name of the models. And then we use Stargazer. We pass the three names of the model. Robust standard errors, we typically don't change that name. I'm going to put the digits equal to 4, and I'm using that the type is LaTeX because the output is a PDF. And then we get the table with results. When you see a table like this, you want to narrow down into the specific coefficients. We know that the price of milk during the rainy season is statistically significant for the three models and is positive. So you want to pay attention to the sign and magnitude of the coefficients. And we already covered in previous video how to interpret the coefficients. We also see that that's the same for catalog. We have positive statistically significant coefficients. Model 1 has the dummy variables for the regions, excluding South as the excluded level. And what we find is that both are positive, but the only one that is statistically significant is center. And as we add pasture, we notice that that is coefficient is positive, but it's not statistically significant. One possible explanation is that pasture and cattle lot may be highly correlated, and that's why the main effect is picked up by the cattle lot as opposed to pasture. So this is one case where we may be concerned about multicollinearity between those two variables. And then the last model also adds family. And as suspected, that coefficient is positive but not statistically significant. Having a larger family doesn't seem to have an effect on income from milk. And then the constant is negative and statistically significant. Now, after looking at the coefficients, and if you were asked to choose what's the best model between the three, you're not going to look at the R square. Why? Because that goes up as we add an additional variable. So instead, we focus on the adjusted R square, which is the best. And what we see is that model 1 has the highest adjusted R square, meaning it has the best fit. So that tells us that model 1 seems to be the best. If we look at the F stat, we don't see much difference. All of them are statistically significant at the 99% level. As expected, these models are better than models with just a constant. So to summarize, when you get a table like this and you want to compare the three models, you want to look at the adjusted R square, and then you want to look at the coefficients and interpret them.